So for this problem, we're asked to use the intermediate value theorem to show that there is a root of the given equation in the specified interval. And the function we're given is f of x equals x squared plus 8x plus 15. And the specific interval we're looking at is -4 to -2. So what the intermediate value theorem is saying is that if we have a polynomial, and we know that a polynomial is typically continuous, so the intermediate value theorem only works for continuous functions. So if we have that, then if we also have an interval, in this case -4 to -2, then we can say that there's another value in between those two where the function will be at 0, aka it will be a root of the function. So for instance, let's try to sketch something that we have on here for this function to kind of give us an idea of what's going on. So let's say this on here is a parabola, which it is because it's raised to the second degree. Let's also say that I'm looking at specifically this interval from -4. So we'll do it from here, -4 to -2. This is the interval that I'm looking at. And given this picture, it's pretty easy to see, at least very straightforward to see, that in this interval, there will be a root somewhere here where it's going to touch the x-axis and hence giving us a root of our equation, right? But we're interested in seeing the values in the y-axis here. Let's just call them C and D. We should be able to tell whether there is a value in between these two. If my C value is either underneath the x-axis, which makes it a negative C value, and the other one is above my x-axis, which makes it a positive D value. So let's try to see if we're able to solve for these. Okay, so the first thing to do would be to plug in some of my values for my interval and see if I get those negative and positive values to the left and to the right of my interval. That would indicate that I have a root between them. So I'm going to first plug in my -4. So f of -4 just allows me to plug in -4 every time I see an x in this case. So -4 squared plus 8 times -4 plus 15. Simplifying this, -4 squared gives me a positive 16. 8 times -4 gives me a negative 32, and then just plus 15. Adding all these values, you get -16 minus 32 plus 15 results in -1, which is that value that we want to be negative or under the x-axis. Now let's try to solve for when we plugged in -2 into our function. So we say f of -2 is equal to -2 squared plus 8 times -2 plus 15. Simplifying this down gives us -2 squared is 4 plus, -16 from 8 times -2, and then plus 15 is equal to 3, which is the value that we want above the x-axis. So at this point, this would be sufficient enough for us to say that since -1 and -3 are between, there's a value between them that will be at 0, aka our root, then as a result, our functions, when we plug in f of -4 and f of -2, have a value between them that's 0. So then we can say by the intermediate value theorem, there exists a C in between -4 and -2, such that f of C is equal to 0. And that c for this function that we have, x squared plus 8x plus 15 equal to 0, has a root within the interval of -4, -2, case with brackets. So we can actually prove that, but most of the problems that you might encounter just want you to show that there's a value between them that will result in that root, aka where it touches the x-axis. The way we would do that is as follows. So in order to show that, we would take our function, I'm just going to rewrite it on here, x squared plus 8x plus 15, and equal it to 0, and try to solve for those x values. So to factor this out, I would use what I would address as the diamond method, where I take my last value and place it at the top, and I take my middle value and place it at the bottom, only because this is a polynomial with a leading coefficient that's 1. If I had a leading coefficient that was some other number, then I would have to take a different approach. But for this one, we want two numbers that will multiply up to 15, but those same two numbers will add up to 8. Those two numbers could be 5 and 3, because 5 times 3 gives me 15, and 5 plus 3 gives me 8. So then I can write them as follows. X plus 5 times x plus 3 equal to 0. And so we factored out this fraction. And so now I can set both of them equal to 0 and solve for x. So subtract -5 on both sides, and I'm left with x equals to -5. And over here, I subtract -3 on both sides, and I'm left with x equals to -3. So to know which one would be our root on here, we would have to see which one matches up with our interval here. Notice that there is another root at -5, but it's not within our interval of -4 to -2. But -3 is within that interval. So in this case, we would say, that f of -3 is R0 within this interval. And that is all. On this next problem, I'm asked to use the intermediate value theorem to show that there is a root of the given equation in the specified interval. The function we are given is x to the 4th power plus x minus 3. And the interval they want is 1, 2. So we're supposed to find a root with this specific interval using the intermediate value theorem. On the last problem that I did, the function given to us was much nicer than this one. This one's to the 4th degree. So in this problem, we're only asked to use the intermediate value to show that there is a value or a root within the specific interval. So we don't necessarily have to solve for that root. So instead, what we can do is we can use the values in my interval and plug them into the function. And if one happens to be above the x-axis and another one happens to be below the x-axis, then I know that at some point they're going to cross the x-axis, and that's where my root is at. So let's plug in first our first value in our interval, which is 1. So f of 1 is equal to 1 to the 4th power plus 1 minus 3. This results in 1 plus 1 minus 3, which gives me the answer of -1, which is that value that's less than 0, and it's below the x-axis. So let's plug in my other value in my interval of 2. So f of 2 is equal to 2 to the 4th power plus 2 minus 3. And this results in 15, which is that value above the x-axis, so it's greater than 0. So we can make the statement now that since -1 and 15 have a value of 0 between them, then there must exist a number c in 1, 2, a specific interval, such that f of c would be equal to 0 by the intermediate value theorem. And then we can say, thus, there also exists a root of the equation, and that equation is x to the 4th plus x minus 3 on the interval 1, 2. And that is enough for us to use the intermediate value theorem to show that there is a root in this specific equation for that interval. That is all.